So I think we're ready to start. One last thing we will discuss about the IP layer today is this field here, which is called the hop limit in IPv6, and TTL, time to live, in IPv4. Right. What is that? It's a number, integer, that is decremented by 1 whenever a packet is routed. And the idea is to have a safeguard against loops. If there is a loop, for example here, if for some reason A sends its packet to B and B sends the same packets back to A. Of course, loops in principle should be avoided in the internet, but as we will see when we talk about routing protocols, the routing protocols are asynchronous. They update the routing tables, not exactly at the same time everywhere. So it is possible that during an update, a loop exists. So what happens if a loop exists? Well, it depends on the bandwidth delay product, depends on the ratio between transmission and propagation time. Here is an example where the propagation time is very small. Then a packet is sent. As soon as the packet is sent, B, if the queue at B is empty, it sends it back to A, which sends it back to B, etc. So we see that a single packet in this case is able to occupy 50% of the link in every direction. Right? In the direction from A to B, we see that this simple packet is almost 50% of the time is occupying the link, a single packet. Right? So of course you will have more than one packet. So if you have routing loops, for all practical purposes, the queues will overflow because you simply have a huge number of packets that are circulating everywhere, and the network is dead. So we cannot avoid totally loops, at least transient loops. So one safeguard is simply to kill the packets that are caught in a loop. So a packet like this, after a very short amount of time, will see that its TTL is exhausted. The rule is that a packet that has a TTL that would reach 0 must be discarded. So when you are a router, imagine for a second you are a router, you have a packet to receive, you receive a packet, and the rules say you should forward it. If by forwarding it you would create a packet with TTL 0, then you must not forward it, you must kill the packet. And if you're a nice router, you will inform the host, the source, by saying, well, this packet was killed because TTL was exhausted. So this is the principle. TTL is the old name in IPv4 in the 70s when it was invented. This was a time. It was time in seconds. Now it's not a time, it's simply number of hops. This is used by Traceroute, for example, and the two versions, the Traceroute and TraceRT. When we discover a path from a source to a destination, in fact, what Traceroute does is send a packet towards the destination with TTL equal 1 to get started. By sending that, if the destination is far away, what will happen? This packet will be killed by the first router. The router will send an error message to you saying, I had to kill this packet. By analyzing this error message, this ICMP message sent by the router, I know who the router is. I have the IP address of the router. So this is what is shown here. I'm doing a trace route to this destination, and I see that my first hop, this is this IP address that has responded with an error message, and of course, the name of this machine, which is this one here, as we have already discussed, was not in the packets I've received, but this pretty printing software has gone to the DNS to do a reverse DNS lookup to know what is the name that corresponds to this address, and etc. Then my Traceroute software, after receiving this, or after receiving 3 responses to the first packet with TTL 1, will increment the TTL 2, 3, 4, etc. And when it receives responses, it has, in principle, the information on the router that is on the second, third, fourth hop on the path. If the path is unique, if there's a single path from A to B, this is the path. Now, if there are equal cost multipath routing, as we will see when we discuss routing, in some cases it is possible that there are multiple paths. If that happens, you're not sure that this is a consistent set of paths. It might be that you receive, for example, the hop 5 and the hop 6 are not necessarily consistent, but if there's a single path used by this flow of packet, you will receive exactly the description of the path. As you have experienced, not all routers send ICMP error messages when they kill a packet due to TTL, so it may be that some of the routers are not shown here. You will see simply empty results here. I skip this, I'll let you discover. Last quiz on the IP module. What happens if I force a host to send a packet with hop limit equal 1? And the correct answer is, of course, D. This packet will never be forwarded by a router. But bridges that are forwarders at the MAC layer, they don't look at the IP header in principle. So a bridge is not prevented from forwarding such a packet, of course. Voila, this is our last point on the IP layer. Are there questions on anything related to the IP layer? If not, then without further ado, we climb down the layer ladder and we go to the MAC layer. What is this image illustrating? Terrible cable management, correct. But it's showing the difficulty of cable management, right? Cables are a problem as soon as there's more than 3 or 4 cables. So you need patch panels and lots of things. This is what the MAC layer is about. Originally, it was about replacing cables by something smarter. So when you have a telephone network, for example, a traditional telephone network is like this. Every telephone is connected by a very long wire to the central office. When we have a MAC layer, which is today for telephony is typically over Ethernet if it's wired, we don't have that. We will have the things that we will discuss now. We will have switches and bridges and the like. We will start by, so the MAC layer is the part of the internet that is the most loaded by history. It is the way it is today because of evolution. And evolution goes to something optimal, but over hundreds and thousands of years. And in the scale of internet, we are at 40 years of existence, so we're not yet at the optimum. Originally, the MAC layer was meant to solve this problem that exists here. So this is the first Ethernet. When I was a student, there was an Ethernet in my office. It was a thick yellow cable that was going from my office. There was a hole through the wall, and it went into the next office. So it was one big cable that went from office to office. Then there was a device to attach your PC to this cable here, when you were lucky to have Ethernet. The first Apple Talk systems were similar. The first, when you had a Macintosh and you threw printers, it was not a big, thick cable. It was thinner cable because Apple is more elegant. But it was the same thing. You simply had cables that you could connect to each other. And those were twisted pair cables. You could simply do a T connection, and it worked. So this is what the mental model it was and continues to be for the MAC layer. So the problem is you have a number of devices, here 4 computers, connected to the same cable, the same physical medium, and you want that the thing work. Now, what is the problem if you connect several devices to the same cable? It is like if several people talk in the same room, you have collision. So how do you handle collision? There's a number of solutions, but roughly 2. One is to do the smarter one, which is used in some cellular telephony technologies. It's called CDMA is one of them. You make sure that you can do some joint decoding by using signals that are orthogonal in some sense. For example, if somebody would speak Chinese in the room here and I continue to speak English, perhaps the collision between the two would not be very large. We create some noise to each other, but by not speaking at all the same language, we reduce the interference. That's the principle of joint decoding. It's done in CDMA, cellular telephony, which is 3G networks. Right? Another element, which is orthogonal to this, is to do exclusion in time. So CDMA is exclusion in code. You can do exclusion in frequency. Here, exclusion in time means you make sure that not two systems speak at the same time. You can do that in a very simple way if you have a centralized system. If you, like me here in the room, I am the center, and in principle you're all very polite, and I thank you for that. If you ask a question, you wait for me to give you the token to speak. Right? That's a polling system, centralized system. But it is not smart enough for computer scientists. They want to do something distributed. So distributed, the idea is that you have 4 devices, they're all equal, it's peer-to-peer, and you want that through some mechanism there is no collision, some magic of some kind. So there are many such solutions. One of them, which is very famous and is not very much used, is Ethernet, that we'll talk about it in a second. And many variants of this has influenced many variants of it. The most probably used today on wired system is power line communication, which is a variant of this. If you use the electrical wires to connect, for example, your ADSL modem from which you receive Swisscom TV to your TV set, so there might be multiple systems on your wires, so it will use a system similar. And of course, Wi-Fi, which is not using wires, but if we see the frequency on which Wi-Fi is running as one channel, then there is the same problem. So Bluetooth, Wi-Fi, and all the wireless technologies are using variants of what we will see here. There is a radically different type of variance that's called the token ring that exists in some very deterministic industrial systems where there is a token that is passing from machine to machine. So you find a way to rank all the machines, order them from 1 to n, and when one machine wants to speak, it waits until a token passes by. When it speaks, it sends its messages. When it's finished speaking, it gives it to the next machine. If it has nothing to do, you will forward it, etc. That's called token passing. But this is not very widespread in outside of industrial environments. What we will describe is CSMA, which is the basis for Wi-Fi and for old-style Ethernet. CSMA is based on ALOA. ALOA is the simplest of all those protocols. So that's the predecessor of 4G and all the wireless cellular telephony networks that we have today. That was in the 70s in Hawaii. In Hawaii, there were multiple islands. There are still multiple islands, and there was one computer in the main island, and some computers in some of the islands. So in total, 3 or 4 computers. That was in the 70s. So, and the problem was to communicate wirelessly from island to island. And the protocol that was invented at that time was managing what we call the upstream link, the uplink. So the uplink is the link that goes from the remote to the center. Because when we go from the center to the remotes, here there's only one speaker. So if there is only one speaker, there is in principle no collision. There is a center. It may decide when it speaks to whom here. But when in the other direction, this may create a collision. If this guy speaks at the same time as this guy is talking, there might be a collision. And on the antennas that receive the signal, the 2 signals are not orthogonal enough, and none of the 2 signals can be decoded. How was that handled? It was this very simple pseudocode that you see here. You send whatever you have to send. You wait for an acknowledgement to come on a return channel. So the return channel is from the center, so it's not subject to collision. And if no acknowledgement is coming, if there is a timeout, you declare that it failed. Probably because there was a collision. Perhaps also for other reasons, perhaps a transmission error or a buffer overflow somewhere, but perhaps also a collision. In other words, it's a very optimistic thing. I send a packet and I cross my fingers. Right? If everything is okay, I will receive an acknowledgement and I know it worked. If it did not work, or if I have a symptom, suspicion that it did not work because I did not receive an acknowledgement, I will send again. Of course, if you do this without this little thing here, wait for a random time, you will create a problem. If there was truly a collision, and if I send again, the other guy will also send again, so we will repeat the collision if we're unlucky, if the timings are synchronized. So to avoid this synchronization, when we detect a collision, we wait for a random time, that's essential, to give a chance to one of the two to win. If there was a collision, the two random times are likely to be very different, so one of them will transmit before the other does. And this is ALOA. It worked as an experimental protocol in the 70s. Remember that at that time, we wanted to send, perhaps we were happy with 10 kilobits per second, so this is how it worked. Now, ALOA is very simple. That's its main advantage. And it's completely distributed. There is no synchronization between the different remotes. But its performance is not good. We can show that this form of ALOA has a performance of 18% of the link throughput. So because of the probabilities of collision, there's an extensive literature that has analyzed this simple protocol. And with a fairly simple assumption, assuming the transmission of packet is purely random, we see that we're able to use the bit rate here only 1/6, well, 80%, 1/2e. So it is not a very efficient protocol. Radio link capacity is a rare resource, so you want to do better. The next thing, but that was an inspiration, and that is what is used always when you have a communication where you really have no way to synchronize the different speakers. So this is used even today in cellular telephony on the signaling channels, for example. When you connect to a base station and you want to start establishing communication, you will use that type of ALOA protocol to first start communicating. Ethernet went a bit further, and Ethernet did a number of changes. First, the first Ethernet that was done was using coaxial cable, like used for TV distribution. And they assumed, for some reason, this property called the medium is transitive. Transitive means that everybody can hear everybody. So if A here sends a packet, everyone will hear it, even the hosts that are very, very far away from A. That was in the requirements of Ethernet. You wanted that any two systems are able to communicate, so it makes sense. On Wi-Fi and wireless network today, it's not necessarily true. If I can talk to the base station and the base station can talk to you, it does not mean that I am able to talk to you directly, because perhaps the distance from me to you is too large, but the distance to the base station is not too large. Right? I can be out of range. So this will not typically be always true in wireless channel, but this was assumed to be true. In fact, you had to make it true for Ethernet to work. And then we can improve a bit ALOA by adding what is called listening, so carrier sense. Carrier sense means that we listen. So what you do is, before sending, if A wants to send, because A can hear everything that's happening, you will try to avoid a collision by first listening whether someone is speaking. This is what you could do typically in a group of friends. If you are a bit polite, you listen before speaking. Right? So this is what you do. You listen. If the channel is free, you send the frame. You wait for an acknowledgement, and the rest is like with ALOA. It may fail, in which case you will wait for a random time and do it again. What happens if we do that? And yes, even if we do that, collisions can occur. And we know why. That's because propagation time is non-zero. Here's what can happen. On short distances, propagation times are small, but still, the bit rates are also very large. So as we have seen, we cannot ignore propagation time. Here's an example of a space-time diagram. A listens, hears that nothing is happening, so starts transmitting. At the same time, B listens, hears that nothing is happening, and starts transmitting. But if the round trip, the one-way propagation time is 2 units, we see that there will be a collision. And if you're sitting in the middle of the cable, if you're here, for example, then you will see a superposition of the two signals in the area where they graphically are superimposed, which might create a collision here. And certainly at A, if A was talking to B, here B will not receive properly, is in fact trying to receive something where at the same time A is talking to him. So it is impossible, in fact, to completely avoid collisions with this system. Even if the bandwidth delay product is very small, the larger the bandwidth delay product, the worse it will be, because the larger times there will be where collisions are possible. But you can never avoid them entirely. So you still need to handle them, which is why we have these acknowledgements. Ethernet is using CSMA, and practically all wireless protocols, except the ones for very, very low bit rate, very deterministic things that use some kind of token passing that I'm mentioning. But practically otherwise, all other wireless protocols use CSMA or a variant of CSMA here. Then with CSMA, the only thing that happens is that the only difference with what we said is that we also observe whether there is a collision. We know that a collision can occur, and then we observe the collision. Not only we observe the collision, but since the medium is transitive, if there is no collision, we know that there is, if we don't hear a collision, we think that we know that there is no collision. So we can save the ACK. We can save the acknowledgement, because if there is a collision, we will hear it. This is the trick, and this is how CSMA CD, which means Ethernet, how it is built. So here a small illustration on how the Ethernet protocol works when it uses CSMA CD. So I'm assuming here A starts transmitting something. The channel is idle, therefore it transmits. And B does the same thing, but there will be a collision because they both are transmitting during this vulnerable period, which corresponds to the round-trip time. So this is a zoom of what we've seen a minute ago. Now what happens if we use CSMA CD? First, we make sure the collision will be visible at A. The collision is at A when A is sending, and B is also sending here. Now, the collision is visible at A. To make sure it's visible at A, when we start detecting a collision, we continue transmitting a number of bits to make it long enough, because to make detection deterministic. But that's a small detail we can skip. So they're called the jam bits. The jam bits are not creating the collisions. We add jam bits because we have seen that there is a collision. So A now sees that there is a collision, and B also at this time sees that there is a collision. So what they do is they draw random times. Now those random times are calculated such that there are an integer multiple of a quantity that's a bit larger than the round-trip propagation time, so that with high probability they will not pick the same, and if they don't pick the same, there's at least one round-trip difference between the two. So here T2 picked the smaller one, and T1 is at least as large as T2 plus at least one round-trip time. So that means when T1 expires, T1 cannot expire during a vulnerable period compared to T2. So here B starts transmitting. Now A continues to listen. So here, in fact, A will start listening, so we'll drop the timer, because now it knows the system is busy, and it has to wait for the system to become idle. So in this case, the collision is not avoided, but is resolved. We avoid repeating it. This is how CDMA works. There's a small catch, though. With CSMA CD, with Ethernet, we assume that collisions are detected at the sources. Here is an example where it would not work. A sends a packet. B sends also, but the packets are very short. The transmission time, which are the vertical times on the vertical axes, are very short. So C will see a collision, because if the intended destination of A's packet was C, then C will receive a packet which is a mixture of the signals of A and B. So there will be a collision, it will not work. But A will not detect that it does not work. Why is that? That's because it's too short. So what Ethernet does, it imposes that this can never happen. It says that we should have a transmission that is always long enough to be as long as the round-trip propagation time. So this is why on Ethernet there is a minimum packet size, which is 64 bytes. And if you keep a given 64 byte at 10 megabits per second, that gives you a maximum transmission that corresponds to a distance of 2 kilometers. If you go, so 10 megabit per second, 2 kilometers, that's something that can be useful. If you want to pull a long cable on a campus and you want to do something very cheap, you can do that. Today, Ethernet is at 100 for cheap thing, at 1 gigabit for ordinary thing. So at 100 megabit per second, the max distance is 200 meters. If you have an Ethernet cable that's longer than 200 meters, this protocol will not work. When we go to gigabit per second, we don't do this anymore. We don't do CSMA-CD. So CSMA-CD, as I mentioned, was using that type of cable. It's useful only in extreme conditions where you want to have long distances and very cheap equipment. Another variant of that is Wi-Fi. This is showing how Wi-Fi works. So it's practically the same thing, except the medium is not transitive. So we do keep a knack, because to detect the collision, we cannot rely on hearing that there's a collision. Here, for example, because A and B want both to send a packet to the base station, but A and C, sorry, both want to send a packet to the base station, but it's not obvious that A will hear the packet sent by C. It might or might not. Also, to mitigate the effect of this non-transitivity, which is called the hidden node, hidden terminal problem of Wi-Fi, there is a small exchange of very short packets, which is called RTS-CTS. RTS stands for ready to send, and CTS clear to send, or request to send and clear to send, sorry. So before A sends a packet, it sends this request to send to the destination, and the destination responds with a broadcast CTS packet. So the CTS packet is sent to everyone. It's sent on the medium, everybody hears it. In particular, C will hear it. So if C was going to send something, C will hear that there's a CTS, and when it hears the CTS, it will back off for an amount of time that is larger than the worst case time it takes to transmit a frame. Of course, there can be bad luck. C might be sending an RTS also, so there might be collisions of the RTS-CTS, but the RTS-CTS are much shorter, so we reduce the impact of collisions here. This is how Wi-Fi differs from CSMA-CD. It's called CSMA-CA instead of CD. We try to avoid collisions, at least collisions of data packets, by sacrificing signaling packets before. But essentially, it's the same. When we do that stuff in Wi-Fi, for example, how many frames can be transmitted concurrently? At least to the base stations. And at least with Wi-Fi as it stands today, it's only one. So the correct answer is the top one, at most one in total. Of course, you could imagine technologies that would have a return channel, an uplink and a downlink that are orthogonal. That happens on cellular networks, for example. But here, typically on Wi-Fi, not. And this is in the mental model of the MAC layer. Also, Ethernet is the same. When we have the old-style Ethernet shared medium, there's only one frame that can circulate at any point in time on the cables. We avoid collisions, but we don't allow two things to be sent together. That's the mental model of the first part of the local area network. Now, Ethernet today is not equal to CSMA-CD. Ethernet, as I said, except for very, very exceptional cases, will not use this coaxial cable. But if you look at Ethernet today at home on your ADSL modem or at EPFL, you will see Ethernet sockets. And behind the sockets, there is a cabling system with boxes. What are those boxes? The boxes are bridges, or so-called switches. For us, it means the same today. A bridge is an intermediate system of the MAC layer. Bridge is the old word, and bridge at the origin meant it's a software system. So the first bridges I've seen were headless PCs with many, many Ethernet cards and a program inside that was doing literally what I'm showing here. Whenever packets come on one interface, the program analyzes the MAC destination address, goes into a table, and depending on the address, sends it on one or the other port. Very much like a router does. So a bridge and a router superficially are the same. They are queuing systems that receive packets on inputs, put them into queues, switch them very fast from input to output, and in order to decide to which output it goes, it looks at the destination address. Except a bridge looks at a MAC destination address, a router looks at an IP destination address here. So the first step in moving away from that, so this was deployed and survived until the end of the 80s, but very quickly people replaced this by switches, which had lots of benefits. In particular, when we use switches, the link between the machine and the switch at the origin was the same as this one, was CSMA-CD, but you realize very quickly that you don't need a collision resolution protocol if the link is only between you and a switch, because the switch will never create a collision. Well, first, there's only one system, so there is no reason to have a collision. And the links are full duplex, which means there is one channel in each direction. You can send to the switch, and the switch can send to you. There is no collision between the two. The typical cabling are those ones. You see 1, 2, 3, 4 wires. There's 2 wires in each direction, so you have 2 different channels. The wires are twisted. Why are they twisted? To reduce interference, exactly. When you twist, you create loops. Neighboring loops are of opposite orientation, so the radiation from the signal that goes from one loop to the next is almost canceled by the next loop, so that the wires do not catch the signal of other systems. Any wire is an antenna. It's receiving and emitting, so this is why here the wires here have a shielding around that avoids this. Here, but shielding is the cables that are shielded are more expensive and more difficult to bend, so cheaper cables are twisted pair. Sometimes you combine the twisting with the shielding. So that was the practically major difference. The plug was different, the cable was different, and the cable is full duplex, which means there is no Ethernet protocol on Ethernet. There is no CSMA-CD on that type of Ethernet, but we need switches. How do switch? So the difference between bridge and switch is only anecdotal. I will use those 2 terms interchangeably. Bridge is a bit obsolete today. If you use bridge, you look old. So the name that is used today is switch. The first difference was when the word switch was introduced, it meant a bridge that is implemented in hardware. The first switches were in software. Then when people did switches in hardware, they were of course faster, they would consume less power, they could be powered even by USB port, etc. So when you did that, you gave a name to it, you call it a switch. But now you find software switches, which are bridges, then this is how terminology evolves. How does a bridge work? Bridge is the correct architectural name. If a MAC layer intermediate system is traditionally called a bridge. Well, as we said, the only thing it needs to have is a table that says for every destination address, what is the output port? Like a router. Except now the MAC addresses, they are completely unstructured from the viewpoint of forwarding. They are structured by manufacturing. So MAC address, the beginning of a MAC address, the first half of the MAC address, is an identifier of the manufacturer. This is why when you do packet traces, you may see, for example, the name of the manufacturer. You may see Apple on the name of your Ethernet interface, but that's not, again, written in the packet anywhere. It is just because the beginning of this MAC address is a signature of Apple. But that doesn't help much to know where to forward the packet. So those tables are completely unstructured, so they are raw tables that have a list of MAC addresses and on which port those devices are. And then the job of a bridge is to be a packet sniffer. It listens to all traffic on all interfaces. It reads the destination MAC address, goes to the table, and repeats the packet on the corresponding interface, like any intermediate system would do. Right. Now the question is, how can a bridge build its table? For routers, we will see that we need configuration in the router to build a table. And if we don't want to do it manually, we use a routing protocol. Bridges, we don't do that. Bridges don't have routing protocols, at least the standard bridges. They must be plug and play. You can buy a bridge at Migros. It's called probably the vendors of the bridge don't even know that they are bridges. For them, they are connecting. It's a multi-port device. So a little box that you can put one Ethernet on one side and 8 Ethernet on the other side. It's a bridge. So it's completely plug and play. You don't go into the bridge to configure it. You don't go into a bridge to configure it because you want it to be plug and play, but also because bridges, some of them, don't even have IP addresses and the like. So it's very cumbersome to talk to something that does not implement TCP-IP protocols. So they're really below the radar screen, the bridges, typically. So how can they build this table? Well, they do it by sniffing. They learn everything they see. When A has a packet to send to B, for the first time, the bridge doesn't know what to do it. So the bridge will broadcast it. It will send to all ports, which is not nice for security and privacy, but this is what the bridge will do. So it will send the bridge to B and to C, but it will send the packet to B and to C, but at the same time, it will remember, it will look at the MAC source address of A, and it will see, oh, I have seen this MAC source address on my port number 1. So A is on port number 1. So we'll put in the table this entry. A is on number 1. Say A was talking to B, now B responds to A, at least if you have a protocol that's two-way. Quasi all protocols are two-way, but there are a few that are not. They're quasi all two-way because usually you have always at least an acknowledgement. So if B sends an acknowledgement to A, then the bridge now knows where to forward the packet, and by receiving a packet from B, we'll see that the source address B is on port 2. So it will build this. So the table is in fact obtained by learning, and of course there will be a cache. Those entries will not be are refreshed whenever you see some traffic. And if A and B don't talk for a long period of time, then the timer will expire, this will be flushed, and you will need to relearn again. So that, in particular, it means that if you very, very quickly change A from interface 1 to interface 3, it will not work for some time, because the bridge believes that A is on 1, and it is not. Question?
I understand that the probability of this event is extremely small, but what happens if two devices with same MAC addresses are connected to a bridge?
What happens if two devices with same MAC address are connected to a bridge? Things will collapse. It won't work.
So, and does it happen in real life? So probably if manufacturers are not somehow synchronized, then it should happen?
Manufacturers, if you are a decent manufacturer, you should request from IEEE what is called an OUI, Organization Unique Identifier, which is a 32-bit string that is the first half of all the MAC address you manufacture. So, and then it's your responsibility as a manufacturer to make sure that two different devices don't have the same MAC addresses. But some manufacturers that are not so high quality cause some problems of that kind. It can happen. If it happens, it's one of those nasty problems where people like you will be needed to debug it, because with Wireshark you will see there are two devices that have the same MAC address, and this system will not work. It will not work because the bridge will learn random things. So if A and C have the same address, A will not be able to talk to B, because when B responds, sends a TCP ACK, it will randomly join A or C, or more likely the bridge will time out after some time and declare that those addresses are too shaky to be taken seriously. So it will not work. Same thing with IP addresses. If you have two devices that use the established TCP connections with the same source IP addresses, the thing will not work. This is why with IP, when we have SLAC, for example, we do address verification. The step 2 of SLAC is to verify that there is no duplication of the address. Question?
So then, for example, if I connect to, if I'm able to modify that address of my device, then I can connect to a public Wi-Fi spot. I can look at the MAC address of one of the devices in a public Wi-Fi spot. I can make my device have the same MAC address and collapse the public Wi-Fi spot.
Whether it will collapse or not, I don't know. That's an interesting thing to try, but it might cause problem, yes. Now, if it's a basic thing, it will collapse, yes. Now, if you buy a Cisco hotspot, for example, it will have a lot, it's verifying a number of things. So if you see addresses that move and go, that you don't expect that address for whatever signature to be both here and there, it will detect that there's a problem and might declare both addresses as invalid. But that might be a denial of service attack against someone else, if you know their MAC address, right? Now, of course, you would like to build a network that has more than one bridge. Bridges are like routers. They're meant to be made in a network. Does it work if I have more than one bridge? So here I'm showing a network where I have 3 bridges. A and B are on B1, etc. And if I, for example, if we apply this mechanism, A wants to talk to D, what will happen? Well, B1 doesn't know what D is, so it will forward it to all 3 ports. In particular, it will go to port 2. So the frame will reach B3. B3 doesn't know where D is, so it will forward it to port 3, and then it will reach here, and then it will eventually get there. So at least it seems that the broadcast will work, but in general, do you think that this will work? Can we simply extend learning to a network of bridges? The majority says A. But here we have an instance, like sometimes in Swiss votations as well, where the majority is wrong. It's true that learning will propagate, and it is true that it will work in this example. But the correct answer is C, only in special cases. And what is special in this example? That is not true in that one. That's the loops, right? That example was a tree. Means there was no loop in it. If there are loops, then you have problems where the propagation will work, but B2 might receive the message from B1 or from B3, and depending on the timing, but also depending on the state of the queues, so in practice it will be random, so B2 doesn't know whether the address A is on port 2 or on port 4, and might oscillate between the two. So there will be a problem if there are loops. How do we solve the problem of loops? We will see next week.